So,
Thank you.
well, we're not quite on time, but that's not bad. It was a brilliant start. Morten, you're up next. Is Morten there? There he is.
Can you see the slides here? Can you?
Yeah, we can see the slides. Great.
Perfect.
So Morten's going to tell us about machine learning, meets nuclear physics. I think the last time we met was on a soccer field playing at the Gordon Conference. Beating Nico, I think I remember. That's my memory anyway.
That's
of course,
true.
on the soccer field of the Gordon Conference. So, this is rather different than the soccer of the Gordon Conference, but I'm sure it's very topical and very interesting about machine learning, artificial intelligence, and all that sort of stuff. So, over to you.
So, thanks so much. This is pretty awesome. I mean, to meet so many people online here. And thanks so much to the organizers for inviting me and for organizing this. It's a great pleasure to be able to present these things. If you're interested, I mean, the aim here is mainly to give a kind of short pedestrian introduction to how you can use machine learning to solve quantum mechanical many-body problems, which has been my cup of tea for many, many years now, and also how you can use these techniques in nuclear experiments and why this could be of interest. It's a pretty new field, and it hasn't taken completely off in nuclear physics. You can peep into the slides. I mean, you have the links here, the Jupyter notebooks, codes and everything, if you want to reproduce some of the things which I'm presenting. I guess the organizers will also upload the videos, so you can actually download everything from that. And if you don't have the time to write down the link, just send me an email and I will just send you the links. In the slides, which you can fetch online, you will also find much more material. We actually run a nuclear talent course on machine learning and nuclear experiment and theory in June and July this year. And we had something like 160 participants worldwide. So the offering this kind of meetings in a virtual way allows you to encounter a much larger audience. And I'd say this nuclear talent course, which we run this summer, was a great success. And we had quite many participants from South Africa, from Africa overall, from Asia, basically from all continents. I mean, populated by humans. So feel free to try out this material, use it as you want. I want to give a kind of rationale for why we're interested in this. So when you deal with many body physics, the computational problems like solving Schrodinger's equations. So one of the problems we really face is this, what we normally call the dimensionality curse. And when you're looking at weakly bound systems in nuclear physics, you normally have to expand your basis sets, which often means that the standard methods, they quickly hit the wall of what is doable. And this is normally called the dimensionality curse. Now, there are many possibilities to circumvent that. You have smarter basis sets, you can have resummations of specific correlations, there are stochastic sampling of high-lying states. There's a lot of activity going on in order to circumvent these problems. For those of you familiar with the shell model, you know that if you would like to, let's say, discuss the calcium isotopes with more than the standard FP shell, you quickly run into the problems that the basis set becomes way too large. So machine learning and quantum computing are then methods which promise to actually be able to tackle this kind of ever-increasing dimensionalities. When we are in particular studying weakly bound systems, this is one of the things we want to do. We want actually to increase the dimensionality of the problem in order to take into account these degrees of freedom. So the very hot field now is actually quantum machine learning. And this is a field which is driven by very young folks. We organized a workshop 3 weeks ago, and the average age of the speakers was between 24 and 40. And there's a lot of activity in these fields in combining both quantum computing and machine learning. So the talk here is basically on machine learning. I give you a short introduction, and what I would like to say something about is also the variational Monte Carlo methods, because in order to give you a kind of overview of how you can use machine learning methods to solve many-body problems, we need some basic inputs from a traditional many-body method, which has been Monte Carlo, variational Monte Carlo methods. And then I also wanted to point to some ways you can actually deal with the analysis of experiments and why machine learning becomes interesting. This field is a huge field. There's been an explosion in software which allows you to actually run many of these machine learning methods rather efficiently and easily. So you have libraries like TensorFlow, which came from Google, PyTorch from Facebook, scikit-learn. These are widely popular libraries. And you can see from the communities of people which develop these libraries that these are communities in the thousands for each set of libraries. And the number of people who contribute keeps increasing all the time. So it's a rapidly evolving field. There are tons of young folks dealing with it. If I wanted to give you a kind of biased kind of view on it, there's a lot of room for creativity. Not all the algorithms can be understood in a rigorous mathematical way. That opens up for a lot of experimenting and trial and error. You need, however, solid command of linear algebra, multivariate theory, probability theory, statistical data analysis, and many of the things you've seen before. And if you think of the job market, familiarity with machine learning methods is almost becoming a prerequisite for many of the most exciting employment opportunities. So you almost have a kind of feeling that if you can spell correctly the words machine learning, you get a job. Now, this was a kind of digression here. Now, if we now look at the types of machine learning which we have, we normally tend to split them into what we call unsupervised and supervised learning. So supervised learning means that things have been labeled and we want typically to reproduce the data. And machine learning is based in a statistical approach called the frequentist approach. That means we are interested mainly in predictions and finding correlations in the data sets. So this should be contrasted to normally what's called a Bayesian path, where you're interested in causation and estimation of, for instance, errors. So there is a big trend nowadays where you try to merge the two. And that leads to something like Bayesian machine learning. So there's a lot of activity here. And the type of problems which you often end up with when you do experiments is a classification, because you would like to classify whether this was a proton, whether it was an alpha particle, what kind of event you saw. And if you're doing theory, on the other hand, you're often more interested in solving a many-body problem, which means a regression problem. And then we have clustering problems, which are also highly relevant when you're dealing with unsupervised learning. So we've been doing unsupervised learning on nuclear physics data, and I will come back to a little bit why this is also an interesting topic. If you have a simple perspective, the way you can look at it, if you look at physics discovery, multi-scale modeling, you want to link that with data analysis, uncertainty quantification, and machine learning theory. This is a kind of perspective of the interface between machine learning and physics. I'm going to rush pretty fast through many of these things here. If you look at nuclear physics, there are now pretty many examples of applications of machine learning in nuclear physics. There have been applications in lattice QCD theory, reconstruction of particle trajectories, design of detectors. That's an important area of applications of machine learning methods in nuclear physics. You have classification problems having application in theoretical nuclear physics like lattice QCD calculations. We have examples of how we can improve the estimation of bias, uncertainty due to the introduction of or lack of physical constraints in the various theoretical models. In theory, we expect to use machine learning algorithms and methods to improve our knowledge about correlations of physical parameters. So deep learning methods like Boltzmann machines and various types of neural networks, they actually promise to, in a way, to circumvent the kind of exploding dimensionalities which you meet in quantum mechanical many-body systems. And they have actually been applied a lot to problems in mechanics, like fluid mechanics, studies of turbulence, because these are multidimensional differential equations, and where you often need to make a very fine-tuned grid if you want to study turbulence properly. So merging a frequentist approach with a Bayesian approach, we often, as physicists, we want to have a probability distribution. So a Bayesian approach is very interesting, and merging machine learning, which is more based on a frequentist approach, where you look after correlations and want to make a prediction, is a very interesting research path. And then you have machine learning and quantum computing, which is a very, very interesting avenue. I have put in the references here. There's several very good articles. There's an excellent one by Mehta et al. Is a physics reports paper. I mean, there are Jupyter notebooks connected with every single figure which they have produced in the paper. So you can, if you want to teach yourself machine learning applied to physics, this is actually an excellent article because it is linked with Jupyter notebooks. So you can actually download the data, download the Jupyter notebooks, run it and reproduce what they have presented. And there's another one by Kaleo and company. And there's actually one of the co-authors is Maria Schult from South Africa, who has written a delicious textbook on quantum machine learning. And she's barely 30 years old. There are many more here. You can actually click on all these links when you have access to the slides. So you can take a look into them. But I recommend strongly Mehta's article. That's a very good starting point if you want to teach yourself machine learning applied to physics. Now, when we look at the basic ingredients in machine learning, there are three essentially basic ingredients. So machine learning is, as I said, is a frequentist approach. You want to make predictions based on a fit to your data. So you have a data set. That's you have an input and you have an output, your Y values, the inputs, the X values. You want to make a model. And this is actually the tricky part. What is a good model? And at the end, you want to evaluate whether this model is a good one or not. And the typical thing you end up with doing then is to construct something which is called a cost function. This is the third bullet point here. And then you want to minimize that one as a function of the different parameters of your theory. So you seek to minimize that function by finding the parameters values which minimize that one. And that leads to various minimization algorithms. So you will be surprised to see that at the heart of every machine learning algorithm, what you have is an optimization problem. That's really the working horse of all machine learning algorithms. So inside there is either a stochastic gradient descent method or some other convex optimization algorithm. But the cost function is the way by which you evaluate the quality of your model. And a typical cost function, which we are very familiar with, is a chi-square per datum, mean squared error, the cross entropy, or other typical functions which you probably have encountered in many physics applications in data analysis. So a neural network is something which is called the universal approximation theorem. That means that if you have more than one hidden layer, one or more hidden layers, you can actually approximate any nonlinear function. And that's something which is very promising when you are thinking of solving Schrödinger's equation. And you could now think of having the complicated correlations being taken care of by a neural network. So this is one of the basic idea with what is going to come pretty soon now. Another thing, if you think of, so recently we had a paper on unsupervised learning for identifying events in active target experiments. And this is an experiment on argon 46. And you see the top part here. So you have these are the raw data. So you can see this is a proton event. And whereas this is a carbon, which comes out from the experiment. And here you have noise. And one of the things you would like to do, since you're now producing terabytes of data, is actually to have a pre-screening using an unsupervised learning algorithm. So this is essentially what we did in that paper, that we use unsupervised methods like autoencoders and k-means method to make a pre-screen of the data so that you can then, when you screen out the interesting events, and then you can do the traditional analysis. But if you have terabytes or even petabytes of data, which is not going to be unusual in nuclear physics now, you have so many events that it's very unlikely that the traditional analysis tools will allow you to perform an analysis in a due time. So this is one of the usefulness of machine learning methods applied to nuclear physics experiments, like these active target experiments where you have tons of data. It becomes simply meaningless for you as an experimentalist to go through almost manually data by data. So I'm going to switch gears a little bit, and I wanted to dive into some of the theory calculations which I wanted to present. So the first kind of theory calculation is actually a simple system, which has been well studied in solid state physics. It's a so-called quantum dot. And it mimics a little bit what we do in nuclear physics, except that the interaction is much simpler. So we have a Hamiltonian with a kinetic energy and a harmonic oscillator trap, which traps these electrons in layers and semiconductors. They interact through the Coulomb interaction. And the thing which is nice, for the 2-electron case, you can even, this is one of the few cases you can solve analytically. So for the 2-electron case, in both in 2 and 3 dimensions, there are analytical solutions of this 2-electron problem. And that is something you can benchmark your codes with. Now, in order to motivate the machine learning methods, I'm going to give a quick introduction to variational Monte Carlo calculation, because that's been the starting point for all the calculations which have been done till now. So in a Monte Carlo calculation, what you have is a trial wave function. And this is your guess, where you bake in all your physics insights about the problem. And you want to evaluate this integral here. And you know from the variational theorem that your guess, if you have the exact wave function, it will normally give you the exact answer for the ground state, or if not, it will be a larger value than the ground state. So this is in its pi of t. People have done variational Monte Carlo calculations. They have been fine-tuning different trial wave functions throughout decades now. Now, these integrals are normally solved by Monte Carlo integration, because the degrees of freedom are way too many for using standard integration methods. And in order to bring this back to a type of statistical approach where you have a probability times some quantity in order to calculate the expected values, you would introduce the standard quantum mechanical probability distribution, where these alphas are now parameters of your theory. So these are variational parameters. And then you want to evaluate this quantity here, and you want to rewrite it so that it looks more like a probability times a quantity from which you want to calculate the expected value. So the standard approach is that you introduce something which is called the local energy, and then you have a quantity which has a probability distribution times the quantity you want to estimate the mean value of, for instance, or any expected moments. And then you want to tune this one by finding the minimum of this quantity in terms of the parameters alpha. So when you do a Monte Carlo sampling, what you essentially are doing, you're invoking the law of large numbers, and then you simply run over a series of samples, and hopefully you have as many as possible so that you can actually run a calculation which gives you reliable results for the energy. And then you minimize this quantity. So the minimization is important, because that one, when you require that to be the minimum, that is something which is going to be used in the machine learning algorithm as well. So you have now, when you do a machine learning algorithm, these parameters would now become the weights and the biases of a neural network. So in a standard Monte Carlo calculation, these are just the typical parameters you would have for the guesses of your wave function. So you need to define derivatives of these different quantities. And when you have these derivatives, so these are just notations which I brought in here. So the thing you end up evaluating is actually, this is the derivative of the energy for one of the parameters alpha. So this is an alpha I, and this is the quantities you have to evaluate. You have to evaluate 2 integrals. So one which has a derivative of your trial wave function divided by the trial wave function times its local energy, minus 2 more integrals. So when you run this with a Monte Carlo calculation, this is obviously something which brings in statistical errors. So there are sources of errors here. But this is actually the way you run a traditional variational Monte Carlo calculation. Now, keep this equation in mind, this one, because that's the same which we are going to use when we now introduce machine learning methods. So these integrals are typically evaluated using Monte Carlo integration and with lots of sources of errors there. When we do machine learning now, one popular path has been to use what's called Boltzmann machines. And they actually received a lot of attention in the beginning of the last decade as a competitor to convolutional neural networks in imaging. Now, they are slightly more difficult to train, so interest was a little bit lost until Carleo and Troyer in 2017 introduced a paper where they actually used Boltzmann machines to perform quantum mechanical calculations. And they looked at both the classical and the quantum mechanical Ising and Potts models. So these Boltzmann machines actually neural networks, and they're normally divided into a visible unit and a hidden units. So the hidden unit is normally called hidden because the output and the inputs are the things which you see, whereas the output from a hidden unit is something you don't see. That's why they're called hidden normally. So you can have, if you look at the figure of a network here, you would now have a visible layer. So these are called generative networks. It's not like a neural network, which you have a fixed input. But in this case, your input are now the coordinates of the wave function or your probability distribution. And then you have hidden layers, and you have interactions between the hidden and visible layers. And these parameters are the parameters you want to optimize. So there will be weights, and there will be biases, A of I and B. So that means that when you now think of it, so you have a function X that represents the visible layer. You would have a vector of M elements. You have a function H, which represents the hidden layer. And there are different ways of doing that. And what you would do now is that you would have a Boltzmann machine, which looks like the Boltzmann distribution. And the way you can think of this now is that this function here is a function now which adds degrees of freedom which you want to fit in a neural network. So we are all familiar with the Boltzmann distribution. And there are different ways of defining this function E. And there are two popular ones. But if we deal with a system like a quantum mechanical system, it's normally a Gaussian binary because you want to have continuous values for the inputs. These are going to be the x's, are going to be the values which you will feed in to the calculation of the wave function. And then you would have the hidden layers, which typically are given by a binary output, could be -1 and +1, 0, 1. And then you have weights, and you have these biases, A and B, which are parameters which you want to fit. And then what Carleo and Troyer did back in 2017 is simply to say that your wave function is given by this probability, or actually your wave function squared. And you can calculate then your wave function here by summing all the hidden parameters. And that gives you what's called the marginal distribution. And the nice thing with these Boltzmann machines, if you keep it this simple, is that you have analytical expressions for the wave function. Now, this ansatz for your wave function, you would typically take the square root of this one in order to define a probability. You can then multiply it, because this would not guarantee the anti-symmetry of your wave function. But you could multiply this with a Slater determinant part, which contains your physics insights. You could multiply this with a Jastrow factor, which now contains your insights about correlations. And then you would let the rest just be parameters which are tuned and optimized in order to get a better estimate of the energies. Or what often happens in nuclear physics is that the wave functions become so complicated that at a certain point you would actually like to automatize the calculation of these quantities. So again, when you want to minimize, the thing which pops up now is that you have a different guess for the wave function, but you optimize the same quantity, which is based on the symmetries of your Hamiltonian and the hermeticity. And again, you have the local energy, except that now your psi is a little bit more complicated object. So that's one way of doing it with Boltzmann machines. If you're interested, you can actually look up the codes which we have and run things if you're interested. Now, let me show you some results for these two electrons here. So if I look at the energy, the ground state energy of this two electron system, this has an exact with a frequency h bar omega equal to 1. It has an exact value of 3. And this is the standard variation of Monte Carlo energy. And you see the difference between a Monte Carlo calculation and a Hartree-Fock calculation. But this is the variation of Monte Carlo energy obtained with a Boltzmann machine. But a Boltzmann machine which now contains only those terms which I showed previously. So you're actually getting pretty close to the exact answer here. And this is a number of iterations you perform in order to reach the most stable result, which then is supposed to be the state which you have when equilibrium has been reached. And you have the most likely state in a standard Monte Carlo calculation, except that now your wave function does not contain all your physics tuning, but it contains a simple Boltzmann machine. You can now see the comparison. So there is the exact result. With this NQS is actually the result which we get from the Boltzmann machine. And this variational Monte Carlo calculation is what you would get with a traditional Monte Carlo calculation. And you see now that the variational Monte Carlo calculation has actually lots of guesses about the wave function based on your physics insights. Whereas the Boltzmann machine here has, this is a neural quantum state, NQS, has essentially no guess about the physics of the wave function. And that's pretty interesting. Now, the other things you see here, something like the the one-body densities for 6 electrons. And there are different calculations. So one is a variational Monte Carlo calculation. And then we have the best Boltzmann machine calculation, where we have a Jastrow factor multiplied with a Slater determinant. So the first result here, RBM, is actually the result with just a plain Boltzmann machine. So there is no kind of deeper physics insights here, except for the Hamiltonian, which drives the system. And what we do next is actually to add some physics insights by multiplying with a Jastrow correlations, which you have from former Monte Carlo calculations, and also Slater determinant, which has been optimized with a Hartree-Fock basis. And you see now that for 6-particle system, you're actually getting pretty close to the variational Monte Carlo results. And that's very promising. However, when you now decrease the frequency, correlations actually become more important in a quantum dot system. And then you start seeing deviations. But still, the calculation, which now has a Boltzmann machine plus a Slater determinant of a Jastrow factor, gets closer to the variational Monte Carlo calculations. Whereas the Boltzmann machine, which has no physics insights about the problem, except that it uses the same Hamiltonian, fails when correlations become strong. So that's an important message, that when correlations are strong, you may need to think a little bit better on what kind of wave function you make. Now, I wanted to give you another calculation, which was done by Adams et al. This is a paper which is on the archive. It was submitted to Physics letter. So what they did was to perform a variational Monte Carlo calculation, but with a nuclear physics Hamiltonian. And in this case, they took the simplest, lowest order nuclear physics Hamiltonian. So where you have parameters, so your two-body force is just a spin-spin plus a central force. And then there's a free-body component here. And the sigmas are the standard Pauli matrices. So this is a potential which you can fit to scattering data. So these low energy constant C1 and C2, they are fit to the deuteron binding energy and also to the neutron scattering length. And these are the parameters which you have, plus this parameter lambda here and D0. So what they did was then to assume, so what they did was to make an ansatz. So the standard way of doing that is that you have an ansatz which contains 2 and 3 body correlations. And these are often highly fine-tuned to the type of nuclear forces which you have. So that's the standard approach. And then you would multiply this with a Slater determinant, which takes into account the single particle degrees of freedom, like we did for the quantum dot case. Now, what they did was actually to replace these with a neural network, with a standard neural network with 4 layers, not a Boltzmann machine, but actually a neural network. And the training goes through the same, essentially the same steps. That cost function, which we discussed, is exactly the same. And then this is actually what you see as a result here. When you look at as a function of the number of iterations for different cutoffs, it's actually getting close. This is for the deuteron. It's getting closer and closer to the exact value, as you can see here. So this is extremely promising. It's a very promising way to replace correlations in nuclear physics. So because if you look at the expression here, this expression 16, normally these contain complicated expressions based on the form of the nuclear forces. So if you can avoid doing that and replace this by a neural network, then that holds great promise for simulating complicated nuclear physics systems where you actually don't know what the correlation should look like. So remember now that when you do such a variational calculation, you actually don't know what the correlated part of the wave function looks like. You bake in all your physics insights. But if you can let the neural network do the job, then perhaps that's a possible way out of this problem with the increasing dimensionality when you add more and more particles, and how do we actually determine the correlations. So I'm getting to the end here, so these are my conclusions. There's a lot of activity here, both for unsupervised learning, for identifying events in active target experiments. There's a lot of interesting works which are done with neural networks on variational Monte Carlo calculations. The problem is obviously the minimization problem. The anti-symmetry is in all these calculations dealt with U multiplying in a Slater determinant, which has been optimized with a Hartree-Fock basis. And then you use the machine learning to determine the correlated part. And the question is now whether we can use machine learning to study correlations in other many-body methods in order to diminish the dimensionality of the problem. So that should end my talk here. So
Brilliant, Morten.
Thanks.
Well, if you stop sharing the screen.
Yeah, I'm going to do that.
Yeah, useful. So that was an excellent overview of the recent trends in machine learning, artificial intelligence, etc. If anybody has a question, please type it in the chat zone. None have appeared so far. I should say that, yeah, there is one now from Jacek Dobachevsky. Great talk, Morten. Thanks. Variational methods are focused on best energy. What about other observables?
So some of the observables which people have been looking at are things like one-body densities and two-body densities, which say a lot about correlation. So that's one of the things you can actually do. Now, one of the other promising things which we have been looking at is in, let's say, in couple cluster theory, is actually to try to use machine learning to make predictions about more complicated correlations like free body correlations. And then try to use that one and bake that in a standard couple cluster calculation, because you have too many degrees of freedom then. So till now we are still stuck with that what you can do when you have the ground state wave function, an optimized one, and calculate observables based on that one.
Thanks, Morten. I should also make a comment that I'm involved in the Agata project and gamma ray tracking, and I know that all these sort of approaches in dealing with the complex gamma tracking in radiation detectors is making vast leaps in the performance of the detector systems. And I should also point out, as you pointed out right at the start, people who are making most of these improvements are under the age of 30, which is
it is. Like
so there's another question. What is it? Please feel.
Hello.
Makito wants to say.
Thank you very much.
Has a question.
Yes. I think the quantum interference is the key. Is a very good point to understand and promote the current framework to forward. Is there any attempt to improve this current framework in terms of the quantum interference? You mentioned in terms of correlations, but I think it is the same thing probably.
Yeah, no, when I think of correlations, because one of the things at the end, when you apply these methods, you want to extract correlations which probably you could not find in traditional methods, or there may be correlations which you haven't thought of. So the many-body correlations which you typically have in a Jastrow factor, so these are correlations beyond what you have in a mean field approach. These are often the difficult things, and at the end, when we are looking at, let's say, a weakly bound nuclear physics systems, and we have a theory which reproduces experiment, then we want to ask ourselves, what is the driving physics behind a weakly bound system? Is this driven by single particle properties? Is it driven by the nuclear forces, and which component of the forces are important for these and these features? Is that the tensor force? Is it the spin orbit force? So the overarching aim here is obviously to get a reliable many-body method, which you then can use to interpret the data and find information about the underlying correlations which drives the physics. That's what we want at the end. So when I was thinking of correlation, this is actually what I think I'm thinking of. Maybe we are not talking about the same things. I'm not sure. Yeah.
Well, I have a feeling that your method works for the case where the Hartree-Fock method can work properly, because in your framework, the wave function is not directly treated. You said that the square of the wave functions are added together to make the total, I don't know how to call it, the wave function. Yeah. But if you square the single particle wave functions for summing up, you erase the information about the quantum interference. That's why
you don't rely only on a single particle degree of freedom. You could actually replace, if you have a strongly interacting system, you could replace the correlated part of your wave function with a neural network. So these Boltzmann machines have become, I think, when people started with the Boltzmann machines, there was quite some excitement, but I think a standard neural network is actually a better approach. The problem, however, is that the neural network may not give you the right anti-symmetry or the symmetry of the wave function. So that's a kind of delicate thing. That's why when we do nuclear physics, we often start, we know that the single particle basis is a very good starting point, and that's a way to bake in the anti-symmetry. And then you let the neural network explore the correlations which come from the more complicated interactions, which you don't account for in a mean field. But you could start with a strongly interacting system and just simply take away the mean field.
So in a sense, this neural network approach is closer to a classical way of seeing the things.
Oh, yeah. Yeah.
Rather than quantum. Thank you very much.
Okay, thank you very much for the questions. Let's thank Morten again. That was a brilliant overview and presentation, and hopes for the future. Thank you very much. To everybody, what I'm noticing on the chat